Hello, so in this video, we're going to be looking at something called the conservation of energy and also the work energy principle. Okay, so in the last two parts of the chapter, the last two videos, we looked at firstly work done. So, work being essentially the energy we put onto an object to move it, right? So, for example, pushing a box forward. Um, the energy we put onto the box in order for the box to move forward, right? And so then we saw that work formula is the force times distance, right? Um, and to remind you, work is in joules or nanometers. Not nanometers, Newton meters. There we are. Those are the units. In particular, you notice the joules because work is a form of energy. Because once again, it's the energy we put onto the object to move it forward. Okay. And we also looked at kinetic energy and gravitational potential energy. So kinetic energy being, well, the energy. So when an object gains speed, so get moves quicker, then it gets kinetic energy, and then gravitational potential energy is to do with as we get higher vertically, higher above the ground. So perhaps climbing up a wall, we're higher above ground, so you have more gravitational potential energy. Okay, because we're against gravity there. Okay, so that's what we looked at really. Okay, so firstly, then we're going to look at conservation of energy, and this kind of does what it says on the tin, really, and it's quite similar to conservation of momentum. So the idea is when an object moves forward, it's traveling, right? That if we don't add on any forces on the object throughout its journey. So if it goes from one point to another, if we keep forces acting on it consistent, right, then the energy must remain the same at the points in the journey. The object can't suddenly gain or lose energy by itself. Okay, only forces can change the energy, but if there's no forces acting on it, then energy remains the same at one point and another on its journey. So what I'm going to say is if no forces, and I'm going to leave this blank, and now I'm going to add on to that in a minute. If no forces act on an object moving, I'm just going to leave it act on an object, then the energy of the object remains the same. Okay? So for example, let's say a car has like, I don't know, 5,000 joules, right? It will always have an energy of 5,000 joules as long as no forces then act on the car. Okay, so the energy will always remain the same. Okay, so okay, so that's the idea essentially that the energy must remain the same unless we add on forces to the object. So no forces acting on the object keeps the energy the same. And so as a formula then, as a sort of mathematical formula, we could say that the gain in energy is equal to the loss in energy. Okay. And so what this is saying is that if we gain some energy, then to conserve the energy, we need to lose that energy as well. So if we gain some energy, then we lose the same amount of energy to keep it balanced, okay? To conserve the energy. And so what that means, I guess, more particularly, we've looked at kinetic energy and gravitational energy. So if we, let's say, gain some kinetic energy, then we have to lose that energy in gravitational energy, okay? So they kind of counteract. We're going to look into that with some examples in a moment to demonstrate that. We could also say, if we want to be a bit more precise, I guess, we could say that the change in kinetic energy add the change in gravitational energy, GPE, has to equal to 0, because then what this is saying is these two changes in energies, which gives me my total change in energy. Well, there is, as we discussed, energy cannot change if it's conserved. So the total change indeed equals 0. Okay. So those two different formulas, two different ways of looking at it, which are the same though. Okay, so that's the idea. Okay. Now, lastly, I'm going to fill this in. So I left it blank for a reason. And so what I'm saying is there's no forces acting on an object, so the energy has to remain the same, apart from gravity. Okay. Or gravitational forces. Okay. And the reason for that is that we already account for gravity in GPE. Okay, so we kind of account for that anyway, and it makes our life a lot easier because gravity affects everything, right? Weight or the gravity is always is always a force acting on any object. So if we already account for that, then that makes life easier. But apart from that, any forces like friction or anything like that, which affects movement, if there are no forces acting on it, then the energy remains the same at all times. Okay. Right. So we're going to look at some examples to demonstrate this. Okay. So here we're told a stone of mass 0.5 kilograms dropped from the top of the tower and falls vertically to the ground, hits the ground with a speed of 12 meters per second. Find the kinetic energy gained. Okay, so if I just draw roughly what's going on, we have a stone, and then we're told it falls down from a tower, right? So it falls down like this. Then it hits a ground. It hits the ground. And so it hits the ground, let's say here. And so we've got these two different points of the journey. We're at the top of the tower here, and then we're at the ground here. Okay. Now, we're also told it hits the ground with speed 12. So I mark that here, 12 meters per second. That's the speed on the ground. But also, quite subtly, we also know the initial speed at the top, because it'll be 0, right? It starts with no speed because it's been dropped from the tower. So it can't have any speed to start off with, okay? And so there we are. So then it wants, firstly, it wants the kinetic energy gained, okay? So that's hinting about changing the kinetic energy, okay? And we looked at this last time, and we know the change is the final kinetic energy, take away the initial, okay? That gives me my change from start to finish, okay? So we know the final speed is 12, so if we work out that kinetic energy, it's going to be half mv squared, or half times the mass, which is 0.5, times the speed of 12, all squared. Then the initial speed is 0, okay, so then it'll be half of 0.5, lots of 0 squared, and that goes to 0, so that means my change in kinetic energy is going to be 36, and that being joules, right? So there we are, okay. And I make a note that specifically the change is a gain, right? Kinetic energy is gained because very simply we are increasing the speed. It goes from 0 to 12. So I make a note this is a gain, okay. Then in part B, it's asking then for the potential energy now, which is gravitational potential energy loss. Okay, so we know that GPE is mgh. Well, we know the mass is 0.5. We know that G we take to be 9.8, just a number. Then H, now H, the height, that's the vertical height. Well, this is the height it falls, right? That's what we want. But we don't have that. We don't have how far down it fell. They don't have the height fell. So what can we do? Well, actually then, this is where conservation of energy comes into play, because if we look at this, what we've just discussed here, we know that the gain in energy is the loss in energy. Okay, so what that means is, if I just note that here, gain in energy equals loss in energy. Well, we know we have gained, as we discussed, the stone gains kinetic energy. However, the gravitational energy is lost, and it says it in the question, it's lost. That is because, again, simply it's gone down. Okay, it's going towards the ground. Its height is lowering. Okay, so that means it's a loss. Okay, so that means the gain in kinetic energy has to then match the loss in gravitational energy. And that's simply what we're going to do. So therefore, we can say that the loss in gravitational energy, GPE, matches the kinetic energy, which is 36. Okay? And that's it very simply. That's the idea of conservation of the energy there. Then in part C, and that being joules if you wish to add that on. Then in part C, then it's asking for the height of the tower. Okay, so we're not meant to know the height yet, but now we need to work it out. But then I'll just go back to what I discussed, that the loss in GPE, the gravitational energy, well, again, it has to be mgh, right? Which we discussed is 0.5 times 9.8 times the height h. Okay, because that's height travelled, right? That's the height. So that's how much energy, gravitational energy there is. Okay. So if you work out 0.5 times 9.8, that will go to 4.9 lots of h. But we know from part B that the loss in gravitational energy is 36. So if we then divide by 4.9, we get h to be 7.35 to 2 decimal places. And there we are. Cool, so hopefully that makes sense. That's the idea. So in this case, we gain kinetic energy as the speed increases. So that has to match the loss in gravitational energy as the object goes down. Okay. Right, let's have a look at this example. So now we're told a particle of mass 0.4 kilograms falls a vertical distance of 7 meters from rest. Calculate the potential energy loss. Okay. So again, we've got this situation where we've got some object that's falling down, and we're told it falls 7 meters. Okay. Now, I'm told I'm told the mass. I'll use that in a moment. But I'm told it starts from rest. And rest, again, remember that means it has no speed. So if it starts at rest, means it has no speed initially. Okay? It starts with 0 speed. I don't know the speed after. Okay, I'll call that V. Okay, I'll call the final speed V. Right. So that's what's going on. Hopefully we can hear. So it wants me to work out the potential energy loss. So again, potential energy is gravitational energy, right? So the change in GPE in this case, well, again, that's going to be mgh. We know the mass is 0.4, g is 9.8, and h, we do know the height. It's gone down by 7, so times by 7. And then if we work that out, we get 27.44 joules. And there we are. Okay. And there we are. So that's the potential energy, and it's lost. Okay, it's lost because it's going down again, right? So it's going downwards, so it's a loss. And so what we'd expect then is that if we're losing this gravitational energy, we expect to make that up with gaining kinetic energy. So then what that means is because we lose GPE, so we lost in GPE, or should I say GPE lost. Actually, no, I'll just say loss in GPE. has to then be the gain in kinetic energy. Okay, these are the only two energies we consider in this chapter. It's, kinetic energy and gravitational energy. Nothing else for now. Okay. Well, we know that the loss the loss is again 27.44. We worked that out. That has to then be the gain in kinetic energy. Okay. And so therefore, it wants me to work out the final speed, but I'll call the final speed V. I just called it V. It's unknown. I want to work that out. Okay, so then I know what the gain in K in kinetic energy is. I can also work that out with these two speeds, right? I also know that the change in kinetic energy is going to be the final kinetic energy. Take away the initial. And so the final speed again is V, so it's going to be half mv squared. Well, the mass is 0.4, so 0.4 lots of V squared. Take away the initial kinetic energy, well, that's zero, because it starts at zero speed. So simply, it's going to be half times 0.4 is 0.2 lots of V squared. And there we are. Okay, but we know that the change or the gain in kinetic energy is 27.44, so that means 0.2 V squared has to match that, right? They're both the same thing. Okay. Right, so then very simply then, I could just solve this for V. So if I divide by 0.2, I get 137.2. So therefore, if I square root that, I get 11.7 meters per second to one decimal place. And there we are. Ignoring the minus from square rooting. Yeah. So there we are.